suppose we're given that z is this function. So we're thinking of z as a function of y and x. Y sine of 2x, 1 plus x squared to the sine of x e to the x squared, and then cosine of x times arctangent y to the 4th plus 1 times log of y to the 6th plus 53. And we're asked to find partial squared z, partial x, partial y at 0, 1. Okay. So we're looking for a second derivative. We call these the mixed partial derivatives because we're going to take a derivative with respect to both variables. Now there's something important to note before we start, is that we are going to evaluate this. So it's not just find the second mixed partial derivative, but it's find the second mixed partial derivative at a particular point. And that actually can make life easier for us. So the key here is to think about, all right, when do we evaluate? Now there's this sort of mindset that a lot of people come in at and say, okay, I should always save evaluation for the end. That's when the evaluation happens. So find the derivative and then evaluate. And the answer is no. No, that's not when you do it. The answer is you evaluate as soon as possible. So as soon as we can evaluate, we do it. But, and this is important, not sooner. So we wait until we can do that. Now, what do I mean by not sooner? So there's a temptation that says, oh, if I can evaluate not at the very end, maybe I should evaluate at the very start. Can we evaluate at the start and then take derivatives? The answer is no. See, we can't take derivatives of something that's not varying. And once you evaluate it, you're said, okay, it's no longer going to vary. It is what it is, and that's it. We're done. So we have to wait until after derivatives until we can evaluate. All right, so let's go through and think about it. Now, first off, because these are really three terms being added together, we can actually handle these separately. So let's start with the first term here, y sine of 2x. So I'm looking for second order partial derivative, so I can think about taking this in two rounds. Partial x of partial y of y sine of 2x. All right, so come to the inner layer. The derivative of y sine of 2x with respect to y, because that's the derivative with respect to y. What do we get? We get sine of 2x, because the derivative of y is 1. So at that stage, sine of 2x is like a constant. Okay, the derivative of sine of 2x with respect to x.
Cosine of 2x,
2 cosine of 2x. And now, here, we'll go ahead and evaluate. And if we do that, plug in x equals 0, y equals 1, what do we end up with? We end up with 2. So here we're going to evaluate both x and y. Okay, so that was the first one. But there's three terms. Let's go to the second term. So, on this term, what do you notice about this term? No y. All right, getting dangerously close to a philosophy class. There's no y. Okay, well, let's debate that for the next 6 weeks. Okay, so if we're taking partial x, partial y, well, that means first take the derivative with respect to y, and then take the derivative with respect to x. If we take the derivative with respect to y, what do we get? 0. Okay, and now that's an easy derivative. In fact, we can evaluate there. Now here, we got lucky. What if, suppose we said, what if we had the following? It was partial y of partial x of this term. What would we do? Well, the answer is we just would swap the order we take derivatives. Because for our class, the order we take derivatives doesn't matter. So if there's an easy derivative to take the easier derivative first. And then life is good. All right. Well, that might be useful to keep in mind as we head into this rather long one. Okay, number 3. All right, so we're taking partial x of partial y of cosine of x arctangent y to the 4th plus 1 times log of y to the 6th plus 53. Now, if we saw this, we'd say, I'm not very excited to take this derivative with respect to y, because there's a lot of y's in here. But what can we do? Take the derivative with respect to x is not too bad. Now, it's not 0 because there's still an x term left, but at least it's easier. So we can say, all right, let's take the derivative first with respect to x, and then the derivative with respect to y. So remember, we go sort of opposite direction. First with respect to x, then with respect to y. All right. And the hard part about this problem is just rewriting stuff. So we have to be very patient as we wait for the copy machine to finish. All right. So what's the derivative with respect to x of cosine of x times arctangent y to the 4th plus 1 times log of y to the 6th plus 53? Yeah. Just take the derivative of cosine of x, it's negative sine x. Everything else is a constant. And now we have negative sine of x arctangent y to the 4th plus 1 log of y to the 6th plus 53. Now at this point we're probably like, all right, we got to take that derivative. Or do we? There was this question up here. When do we evaluate? Now I said we can't evaluate before we take a derivative. Well, let's think about what's happening here. Notice that there's 2 variables in play. There's x and y. And we're taking the derivative with respect to x, and we're taking the derivative with respect to y. Once we've taken the derivative with respect to x, we no longer need to let x vary. So what can we do? We can evaluate at that point. So I don't have to wait until after I finished all my derivatives to do my evaluation. As soon as I'm done with derivatives with a certain variable, I can say, aha, time to evaluate. So we're going to evaluate not both the variables, but just the one that we no longer can vary. So evaluate x equals 0, and say this is going to be the same as partial y. Well, what happens when I plug x equals 0 in? I get 0, because sine of 0 is 0. And that's a nice derivative. And now, of course, I can evaluate here at y, and I get 0. So what's the answer? Well, it's the 3 pieces added together. So we get 2 plus 0 plus 0. So our final answer is 2. All right. Good. Now, on to today. So today, it's action-packed, full day. So we're going to talk a lot of different ideas, but they all sort of start from the same place, which is we're going to talk about differentiable. Now, when we talked about differentiable in Calc 1, there sort of was this notion that says, differentiable, that means I can take a derivative. Okay, that's actually a pretty reasonable idea. But there's another notion of differentiable which says something is differentiable if locally it looks flat. So that means that you could take your function and you could zoom in. And you could zoom in, zoom in, zoom in, and if you zoomed in close enough, it looked like a straight line. All right. Well, we want that to be the idea of differentiable for multivariables. So if I have a function z equals f of xy, now normally what do I see is I'll see a surface with sort of bumps and wiggles and all sorts of things. But I want to zoom in and zoom in. And what do I want to see when I zoom in? Well, I want to see a flat thing. What's a flat thing to a surface? A plane. Yeah. So what we'll have is we'll say that for us, differentiable says when we zoom, we see a plane. So we see a flat thing when we zoom in. Now, we have to be careful. We have this notion of derivatives that we talked about last time, which is this sort of partial derivatives, saying what happens as I vary x, and what happens as I vary y. And so I can look at that and say, okay, what is happening? And the question becomes, is it enough to have partial derivatives to be differentiable? And the answer, well, is no. So let's take a look at a function. Suppose I have the function f of xy is the square root of the absolute value of x times the absolute value of y. This function is defined for all values of x and y, because the absolute value means I'll never take a square root of a negative. So suppose we want to find these things. So if I want to find partial f, partial x of 0, 0, what do we do? Well, what this says is, notice that this says, see what happens as I vary x. So to find partial f, partial x at 0, 0, we look in the slice where y equals 0. Because that's what we do. We take partial derivatives by looking in slices. And the slice we're going to look in is according to what the other variable does. Now, in the slice y equals 0, what happens to my function? What does f of xy become? It becomes 0. So I shouldn't say f of xy, I should say f of x is 0. So I'm in that slice. I'm in the slice where y equals 0. When I take that derivative, the derivative with respect to 0, what do I get? Sorry, the derivative of 0 with respect to x, we get 0. So what happens is when I take that slice, when I look in that cross-section, I'm seeing a very uninteresting function. I'm seeing a function which is constantly 0. What happens if I do partial f, partial y at 0, 0? Well, in this case, because I'm taking the derivative with respect to y, I want to hold my x variable fixed. So my x variable says, look in the slice where x equals 0, because I'm looking at the x fixed. So I'm looking at f of 0 comma y, which again is 0, and that derivative is 0. So my partial derivatives say, oh, it's uninteresting. Nothing's changing. But what does the function look like? Well, the answer is the function looks a little bit like that. And it's maybe not the easiest to see in this picture, but what you're seeing here is it's like been pinched. So along here, this is the x equals 0 line. Wait, is that? No, let's see. X, yeah, it is. X equals 0. And along this line here, that's the y equals 0. And as you can see, it's not flat. It's actually very unflat. And no matter how far you zoom in on 0, 0, it's going to be, you're going to see this pinched behavior going on. So having the partial derivatives is not enough to be differentiable. But it turns out it's almost enough. So what does that mean? Well, if we add another condition, which says not only do you have the partial derivatives, but they're also nice in that they're continuous, then you have enough to be differentiable. See, the problem is if you try to take your derivatives here, f sub x and f sub y, what you'll end up with is something which is very uncontinuous or non-continuous. And so that's going to be an issue. So how do we justify this? Well, here's sort of our intuition. Let's look at f of xy minus f of ab. And what we want it to do is we want it to be flat. In other words, we want it to behave like a flat thing should. We want it to behave like a plane. So we want to somehow argue that what's happening is like a plane. Now, we're going to do our classic add and subtract. So I take my f of xy minus f of ab, and I'm going to add and subtract a term in the middle. In this case, it'll be f of xb and minus f of xb. Now, why that term? Well, that term in some sense is sort of like a compromise. You can say, well, both the entries here differ. So here I have xy, here I have ab. But notice that in the first case, the x's agree, and only the second entry differs. In the second case, the b's, they agree, and only the first entry differs. So by adding and subtracting, we get to say, okay, we have two pieces, but in each piece, I'm only having one thing change. So that makes it easier. Now what happens? Well, we're going to look at these two pieces a little bit closer. And here we go. In the second piece, that's probably the easier piece. It's a little small, but let me just read it out. What's happening here is I can think of it as my b is currently fixed. And if I want to understand what's the difference between f of xb and f of ab, well, the answer is I can think of b as being a constant, and I can say, okay, multiply the f sub x at ab, which is the rate of change of how does a function change as x changes, times the amount of change, which is x minus a. In other words, this is the type of idea that we use from Calculus 1. We say if I want to know how much the function changes in the output, I take the derivative times the change in x. That's an approximation for how much the function varies. Now the approximation, of course, gets better the closer we are to the point, and that's the idea of zooming in. Now for the first one, there's sort of two steps. We say, hey, you know what? We can say that it's a similar idea. This is approximately the derivative f sub y at xb times the difference y minus b. But then we say, wait a second, f sub y is continuous. And I'm going to assume that x and y are both close to a and b. So f sub y at xb is about f sub y at ab. So here's the punchline. Near the point AB, we get the following, that f of xy is approximately the value of the function f at AB plus how much the function changes with respect to x at the point AB times x minus a plus how much the function changes with respect to y at AB times y minus b. So what's happening? Well, the right-hand side, this is going to be our big idea, and we're going to keep coming back to this again and again and again. We're going to get a lot out of this idea. So that's the linear approximation to our function around the point AB. And it's also the tangent plane. Because if you look at it, it looks a lot like what we'd expect a plane to look like. All right. So this is good. In fact, this is a really great, it matches what you would think intuitively should happen. If I want to know the value of the function at a point near AB, I say take the value of the function at the point AB and estimate how much I've changed due to how much I vary in x and how much I vary in y. All right. Well, so where do we go? So what we're going to do is we're going to look at this term for a second. And we're going to call that our tangent plane. So what have we done here? So we have this surface here, this blue surface. I'll call this z equals f of x, y. And I have a particular point marked. So down here, this point down here, this is at the point A, B, which is to say x equals a and y equals b. So there we have our setup, and we're interested in saying what's happening to the function around this point AB. So I'm interested in what's the behavior of the function around here. Well, if you zoom in, the function should look flat. And the claim is that that flat thing is a plane. So how do we justify that? Well, what we did is we've copied down the linearization, it's a hard word to say, linearization, the linearization from the last bit. All right. Now let's think about what's happening. Suppose I'm going to fix for a second, let's fix x. So here's x equals a. And if I fix x equals a, I see a slice. So it's like I've gone through and I've sliced my function. And the slice I see is this slice down here. And what happens? Well, if I slice, I also don't just slice my function, I slice my tangent plane. And when I slice my tangent plane, I get a line. And that line should be the tangent line. Well, let's take a look. In the x equals a slice, what happens? Well, I get f of ab plus f sub x of ab times a minus a. What happens to that term? It's 0. Plus f sub y at ab times y minus b. So I see in that slice I get z equals f of ab plus f sub y of ab times y minus b. That's exactly what we should get for the tangent line to this curve. Because this curve right here, this is the curve z equals f at a comma y. So we see, aha, that matches what we should think should be true, which is good. Things should match. If we slice in the other direction, so say we hold y equals b fixed, then on the plane, we'll see one type of behavior. And when we translate that down, that part of the plane that we slice into is going to become the tangent line. Now, on this line here, we got it by holding y equals b. Now when you hold y equals b, the other term drops out. So you end up with z equals f of ab plus f sub x at ab times x minus a, which again, that's what you should get, because this curve downstairs, this is z equals f of x comma b. So that's good. So the tangent plane matches sort of the intuitive thing that was going on before. We said, hey, when we took lines in the cross-sections, those tangent lines, those two lines should be part of a tangent plane. And the answer is that they are. And we don't have to do anything fancy. It just pops out. So finding tangent planes is nice and easy. And that's our favorite kind of thing, nice and easy. All right. So we're going to come back and talk more about tangent planes. But first I want to talk a little bit about the chain rule. Now, what's our goal? We want to do the chain rule for multivariable functions. The chain rule is a really nice idea of having a function inside of a function. And we got a lot of use out of it. So what's going to happen for us? Well, let's talk about an example just to sort of get us going. So what was happening before with the chain rules, we'd have something like f of g of x, which was okay. But now, of course, more interesting things could happen. So I could have z, it might be a function of x and y, but then x and y might be functions of t. This isn't so hard to imagine. We could easily come up with a scenario. So for example, we could think of z as being an elevation, and x and y as being a location. And so what happens is that the x of t, y of t, it's like you're moving in the two-dimensional plane below, and your f is the height above that point. So these are reasonable types of things to look at. Now the way that I like to think about variables, and I encourage you to think about them as well, is to do a diagram which shows how the variables relate to one another. So here we see that z, well, it will depend on x and y. So z depends on x and z depends on y. And similarly, x and y both will depend on t. So we draw a line. So as we go from top to bottom, we see how the variables relate. And in particular, you should see that there are two t's downstairs. So what's happening? Well, that says that t is influencing our top variable z in two different ways. So there's an effect through the variable x, and there's an effect through the variable y. And in some sense, we have to capture both. Now, how are we going to go about doing this? So we start with our linear approximation. So we start by saying, I have this thing called f of xy minus f of ab, and that's approximately partial f partial x at ab times x minus a plus partial f partial y at ab times y minus b. So far, no big surprises. Now we can give things some better names. So f of xy minus f of ab. What's that measuring? What does that correspond to? Any ideas? How can we think about it?
Limits.
Well, there will be limits in a minute. But first off,
That's your height at that.
well, they're heights, right? But notice that we're taking a subtraction. So what does it do when we look at subtraction? It's like change. So this right here is the change in your output, which is the change in z. X minus a, what is that? Change in x. Y minus b? Change in y. So we can simplify our notation, say the change in z is approximately the derivative of z with respect to x times the change in x plus the derivative of z with respect to y times the change in y. It's just another way to express this notion of linear approximation. Now we're going to do something not very surprising, which is divide everything by delta t. So we can say that delta z over delta t is approximately partial z partial x times delta x over delta t plus partial z partial y times delta x over delta t. Oh, sorry, partial z partial y times delta y over delta t, excuse me. Well, what's our next thing to do? Where do we go? Now we go to limits. Limit says what? Well, as delta t, oh, well, that's a weird typo. That should be so. Let delta t go to 0. As we let delta t go to 0, our approximation goes to an equality. Because the approximation gets better the closer you are. So as delta t is getting closer to 0, we're getting closer, approximation gets better, and therefore we get the following. dz dt is equal to partial z partial x dx dt plus partial z partial y dy dt. Now we should pause for a moment here and think about our choice of notation. And in particular, why do we have a d? Because we've been talking about this partial notation. Because you'll notice that there are some places where we have a partial symbol. So for example, over here, we have a partial z partial x. Over there, though, we have a dz dt. So what's the difference? When do we use the d versus when do we use the partial? Do you remember? Well, we used the partial when they were mixed, yes. But what's the key? What's the difference between when we use the d versus when we use a partial? Okay, so it comes down to how many variables are involved. So, for instance, x and y are functions of a single variable t. So that's why we use the dx dt and the dy dt. Here, when we're thinking of z, what we're really thinking of is the following. We're really thinking of z as itself a single variable function. Namely, we can come back up here and say, well, z of t, that's f of x of t, y of t. Which means that there's really, I'm thinking of z as only depending on t. And since z only depends on t, therefore I can say, aha, it's a function of a single variable. That's why we use the d notation. So we use d when we think of a function as a single variable. We use partial when we think of our function as being functions of multiple variables. So this partial notation here, partial z partial x and partial z partial y, is focusing on this z equals f of xy. Where there I'm thinking of z as a function of more than one variable. All right. In terms of the tree, there's a nice way I like to think about what's going on. So notice we have a plus here, and so there are two terms. But we also notice, hey, there are 2 times t shows up. That's not a coincidence. Essentially, the number of times that t shows up in that tree is how many terms you'll end up with downstairs in this expression. So we had t show up twice, so we had 2 terms. If we had t show up 5 times, we'd have 5 terms. It would be a more interesting tree. And we can look and say, okay, let's look at the pieces. So if I want to understand how things are changing, well, here, if I'm looking at x, depends on t, I would say the way that x changes with t is dx dt. And if I want to ask how does y change with t, well, it's dy dt. And these are single variable functions, which is why we use the d. Now let's go to our next layer. How does z change with x? What's the answer? How would we write that notationally? Partial z, partial x. And the reason we use a partial symbol here is because z has two inputs. How does z change with y? Partial z, partial y. Now, how do I get the answer? Well, follow the tree. So for every time I see a t, I start at the top and I work my way down. So I say, okay, here's a partial z, partial x, dx dt. That's my first term. And then, partial z, partial y, dy dt. That's my second term. And I'll add them all together. So essentially what's happening is I want to understand how does t affects z through x, and how does t affects z through y. I add the two results together, and that's what we get. Let's do some examples. All right, some warm-ups. So sand is pouring out, forming a cone. And at a particular moment, the rate of sand flowing is 10 pi cubic feet per minute. The radius is 3 feet. The radius is changing 1 feet per minute, and the height is changing 2 feet per minute. What's the volume of sand at that moment? So we have to understand the picture here. So it's forming a cone. Now, it doesn't tell us the cone, but odds are pretty good it's going to look like this. So a cone looks something like that. And so we have some sort of conveyor belt where sand is coming down and forming a little pile. Most piles of sand do not form in the following way, where you have sand pouring down on top. That's not how sand forms. So pretty sure that's what the picture should look like. Okay. I should have used my sand-colored. Okay, we'll make it sand-colored. There we go. Now it looks more sand-colored. All right. So what do we have? Well, we have a lot of information here. So let's sort of parse it. So we want to translate all these things into our notation. First off, the one thing that the problem doesn't give us is a volume. So volume of a cone is 1/3 the base. Well, the base is a circle, so it's pi r squared, and the height, where the r is the radius of the base, and the height is the height of the cone. So that's the formula for our volume. So let's go through and see what we have. And we're going to, every time we see a number, we're going to try to understand that number. All right. So at a particular moment, the rate of sand flowing is 10 pi feet cubed per minute. What is that 10 pi measuring? It is a rate. So, well, what rate is it? What is it? Well, it's a rate related to volume. Sort of the hint is the cubic feet. So how do we denote 10 pi? What does that equal in terms of things that we have written down? It's dV dt. Change in volume with respect to time. So we're told that dV dt equals 10 pi. The radius is 3 feet. What does that translate into? Well, radius equals 3. Because we're using our variables are r and h. The radius is changing 1 feet per minute. What is that? dr or dt. So when we're talking about change, that's another word for derivative, equals 1. The height is changing 2 feet per minute. What is that? dh dt. That equals 2. Now, we look at this and say, okay, this shouldn't be so bad. We have R, we just need H to find volume, because we're asked what's the volume. The thing is, we don't have H. So it feels like we're kind of stuck. How do we get unstuck? Well, what we should think about is we say, well, we have all this information given to us about rates, and so we should use that information about rates. So what do we have? Well, we have volume, which depends on R and H, and then we have R and H. Well, they're changing with time. So I can think of there being a diagram here where I have my variables related in this way. So we can say that by the chain rule, the change in volume with respect to time is the derivative of V with respect to R times dr dt plus the derivative of V with respect to H times dh dt. So this is the chain rule. We're just using different symbols. So instead of x, y, and z, we're using r, h, and v. Well, that's okay. Symbols are malleable. We can change them to be what we want them to be. So we're doing this because we say if we have information about derivatives, we've got to put it into something that looks like derivatives. So now let's go through and put in what we know. dv dt, do we know that? 10 pi. How about partial v partial r? Yeah, come here, take the derivative with respect to r. That would be 2/3 pi rh. And we'll fill that in a minute. dr dt, 1. Partial v partial h. One-third pi r squared. And then dh dt, 2. Now we say, okay, what do we know? Well, we know r. We know r is 3, so we can plug that in. So if we plug that in, we'll get 10 pi, 2/3 times pi times 3 becomes 2 pi h. Then I have 1/3 times pi times 9 times 2. So that would be, I believe, 6 pi is what it should work out to. What can we do? We can solve for h. So, for example, if I subtract 6 pi, that would be 4 pi equals 2 pi h. So what does that say about h? So h equals 2. So it turns out we were able to use rates to help us solve for the variables. Now, is that our final answer? No, because we're looking for the volume. But we already knew r, and now we have h, so we can plug it into our volume formula. So we get 1/3 pi times 3 squared times 2. And if we work that out, that's a number. I think it's 6 pi. There you go. Okay. Should put in some lines here, separating the ideas. All right. So here's another example. Suppose we're given that z is equal to x times y. All right, that's a pretty simple function. X is some function f of t. Y is some other function g of t. Use the chain rule to find dz dt. So here, there's nothing very surprising here. So let's just go ahead and work this out. So z is a function of x and y. These are functions of t. So the chain rule says that dz dt is equal to partial z partial x times dx dt plus partial z partial y times dy dt. Nothing too surprising. What is partial z partial x? So come up here. Z is x times y. Derivative of x times y with respect to x? Well, I'm asking that question because if we don't know what that derivative... Oh, wait, no. You meant y as in the variable y. That is correct. So y dx dt plus partial z partial y is x. Oops, that's supposed to be a t. dy dt. All right. So far, you're just like, okay, all right, whatever. But let's actually see what this says. So let's talk about let's talk about z. Z is x times y. X is f of t. Y is g of t. F of t times g of t. Well, I can write that as f of t times g of t. What is y? Well, y is g of t. What is dx dt? It's f prime of t. So that's f prime of t, g of t, plus x, which is f of t, and dy dt is g prime of t. Does this look familiar? This is the product rule. So what does that mean? Well, that means now you have one less rule to remember. You can say, look, I don't need the product rule anymore. I'll just remember the multivariable chain rule and rederive it. Okay, or not. Or you can remember both. But it's kind of nice. It sort of says, okay, this is consistent with things that we've seen in other places and in other settings. All right. Now we can, of course, handle more complicated relationships in a similar fashion and just work the diagram. So I could have here z is a function of x and y, but now x and y are actually changing with two variables, s and t. And if I want to find the relationships, what do we do? Well, the answer is we just read the diagram. So let's read the diagram. So partial z partial s and partial z partial t. Now notice we're going to use the partial symbols here because at the end of the day, what does z depend on? Well, the answer is you go down to the bottom and you see what shows up. Now previously we were in diagrams where we just had t at the very bottom, which meant we only depended on one thing. But now we have two things at the bottom, s and t. So we depend on two things. So to help read the diagram, you can populate it by saying, okay, I see that z depends on two variables, so I put partial z partial x, partial z partial y. I see y depends on two things, partial y partial s, partial y partial t, and similarly, partial x partial t, partial x partial s. So if I'm looking for partial z partial s, I say, let's find all the s's. There they are. There's two of them. And now we just read the diagram. So partial z partial s, I follow, there's an s down here, so I follow the chain down. So it's partial z partial x times partial x partial s. So boom, boom. Plus partial z partial y times partial y partial s. Again, it's down here, follow it down. The proof works the same as the chain rule we talked about. In fact, really this is the same chain rule. We're just saying, think about holding t fixed or think about holding s fixed, depending upon which derivative you want to look at. For t, very similar process. So there's two t's. You say, all right, follow them both down. So partial z partial x times partial x partial t and partial z partial y times partial y partial t. All right. Well, let's do something a little bit more interesting. Suppose we have z equals f of x, y, t, and x is also a function of t, and y is a function of t. So this is a little bit more complicated. So let's see. We have z, which is f, and that depends on x, y, and t, and x depends on t, and y depends on t. Now, it's a little bit more complicated notation because we want to be careful to make sure we understand what derivatives we're talking about. there's also, you might say, well, wait a second, the t's are at different heights. Is that okay? And the answer is it's fine that they're at different heights. That won't stop us. So what do? Well, we read off the diagram. So I'm going to make sure we don't confuse ourselves too much, instead of using z's, I'm going to use f. So I'll say here, this is f sub x, derivative with respect to x. The next one over is f sub y, and the last one here is f sub t. That way we don't confuse ourselves. Down here, again, I can use the subnotation y sub t, and I can use x sub t, or I could say x prime, y prime, but that's all right. So what do we get? dz dt, which I'll say z sub t, is equal to f sub x times x sub t, derivative of f with respect to x, derivative of x with respect to t, plus f sub y times y sub t plus f sub t. Again, follow each branch down. So there's one last idea. And we're just going to have to power our way through this one. So our last idea is, this is a big day, this idea of explicit versus implicit. Now, most of the times when we deal with functions so far, we've dealt with things which are explicit. And explicit means that if I have z equals something that involves x and y. So it's like I'm given a recipe. You give me x and y, I do a bunch of manipulation with x and y, out comes my z. Very straightforward. Implicit relationships are ones where there's not a clear relationship. It still depends on what x and y are to get z, but it's not so clear how to get z. So as an example, e to the z plus sine of x times z equals cosine of x minus y plus 5y. If I plug in choices for x and y, I'm limited to what z can be. Usually I'm limited to 1, maybe 0 options. Sometimes there's multiple. But I'm limited, I'm restricted. So z depends on x and y, but now we don't have our clear relationship. Well, if z depends on x and y, we can still ask the question, what happens to z as we change x and y? So in other words, what's the derivative of z with respect to x, and what's the derivative of z with respect to y? Now, the answer is think of z as depending on x and y. So if we think of z as a function of x and y, we say, we don't know what that function is, but we can still think of it as there being one. And once we have that idea, the rest is pretty straightforward. So, what can we do? Suppose we start where we have some relationship. We've moved everything over to one side. So I have something which says f of x, y, z is equal to 0. So that's my relationship. That's my implicit relationship. And now we're going to think of z depending on x and y. So if I want to understand my relationships, I say, well, okay, f depends on x, y, and z, and then z, that depends on x and y. All right. So what? Well, take the derivative. So taking the derivative of both sides with respect to x, well, the derivative of 0 is 0, so that's easy. If I want to take the derivative with respect to x, I see x shows up in two places. So f depends on x directly, but it also depends on it indirectly through z. So I get f sub x is this branch, plus f sub z times the derivative of z with respect to x. That's the second branch. So that's the derivative of the left-hand side. And so you can rearrange and get partial z partial x is negative f sub x over f sub z. You can do the same thing with respect to y. And if you do that, you get that partial z partial y is negative f sub y over f sub z. The key idea is you always treat z as a function of x and y, and then take the derivatives. Even if you don't explicitly write it down, in your mind, that's how you think of it. Well, let's do an example. So what's the mindset? Remember what we have going in. So suppose we want to find partial z partial x and partial z partial y, given that we have this relationship. Z plus e to the power xz plus sine of x times y plus y cubed equals 17. Look, right now, it's hopeless. Hopeless. You're never going to be able to solve for x or for y or for z as a function of the rest. There's just no way to do it. So how do we find these partial derivatives? So remember, what's the idea? So the idea is we want to find z in terms of x and y. And the way we can tell that is we're looking at the notation. Partial z, partial y says, what is z doing as we're changing y? So we're really thinking, okay, we want to know what z is. So here's the key idea. We don't know what z is, but we're going to pretend like we do. So we're going to think of z as being a function of x and y. Now we don't explicitly write this out. This is sort of done in our minds. So in other words, as we're sitting here doing math problems, we say to ourselves, in our minds, we're going to think z equals z of xy. That's what we're going to think. Now, because it's hard for you to see what's happening in my mind, of course, I'm doing math, so I'm happy. But in general, let's try to see what we would do. So when we were reading this, we were really thinking of it in the following way: z, which will depend on xy, plus e to the x times z, which depends on xy, plus sine of x times y, plus y cubed equals 17. So, let's start with this one. We're going to take the derivative of both sides with respect to x. We know it's with respect to x because we look in the denominator. So, taking the derivative with respect to x, what do we get? Well, let's go through our terms. So z. Now it looks like there's no x there, but remember, in our mind, z of xy. So z does depend on x and y. So we say, okay, so what is the derivative of z with respect to x? And the answer is, the derivative of z with respect to x is the derivative of z with respect to x. Okay, that's pretty good. Now, e to the xz, well, chain rule. So, plus e to the xz, then we're going to times it by the derivative of xz. And remember, it may look like there's only one x, but in our mind, z depends on x. So product rule. Derivative of the first is 1 times the second. So 1 times z plus the first times the derivative of the second. And that's the derivative of z with respect to x. And what does that turn out to be? The derivative of z with respect to x. Now we go to our next term. The sine of xy. Well, that one's not so bad. Derivative of sine is cosine. Then I times it by the derivative of xy with respect to x, and that would be y. Derivative of y cubed, 0. There's no x's. All right, and so that's the left-hand side. The right-hand side, 0. Now, if we've lived a good life, well, we have lived a good life. We're good people. And if we have, what we'll be able to do is, at this point, we can solve for, say, partial z partial x. So here, I see there are two partial z partial x's. And what we do is we take all the terms with the partial z partial x, and we put them together on one of our two sides. So partial z partial x, and then we have plus x e to the power xz partial z partial x. And that's going to be equal to, well, this term, but then moved across. So minus z e to the xz, and then here, minus y cosine of xy. So the partial z partial x, okay, we can factor that out. Partial z partial x, 1 plus x e to the xz. And finally, we want the partial z partial x by itself. So we get that partial z partial x is equal to minus, and I'll actually factor minus out, z e to the xz plus y cosine of xy. Divide that by 1 plus x e to the xz. Okay, and there we go. There we go. That's the answer. Now, it might be helpful for us to just take a second and compare that to what we said the answer should be. So we have here the partial z partial x should be minus f sub x over f sub z, where f is this whole expression. So this is our capital F of x, y, and z. So let's check if that's true. If we take minus f sub x, so now we're just thinking of x, y, and z as independent temporarily. Well, what would we get? Well, there's an x here, so by the chain rule it would be z e to the xz. There's an x here. That would be y cosine xy, and that's it. Downstairs, take the derivative with respect to z. Well, there's a 1, and then the derivative of e to the xz is x e to the xz, which is exactly what we have from this formula. Now, what's the punchline? Well, you can either remember the formula or remember the process. And for me, I prefer remembering the process because it's just as fast. And oftentimes I find I'm less likely to make a mistake. Now we're only halfway done, which is good. You know, that means we can smile. There's more to be done. What's the other half? Well, partial z partial y. What is that? Well, we do the same thing, but now we're going to think of it in terms of with respect to y. So again, reading through, derivative of z with respect to y, well, that's partial z partial y plus, well, e to the xz. Well, is there a y? Well, yes, inside of the z. So that's going to be e to the xz times the derivative of xz with respect to y. Well, the x is a constant, and then the derivative of z is partial z partial y. Sine of x times y, well, that'll be x cosine of xy. And finally, y cubed, that's 3y squared. And that's going to equal the derivative of 17 with respect to y. Well, when we took the derivative of 17 with respect to x, it was 0. But when we take the derivative of 17 with respect to y, it's still 0. It's still not changing. Okay. Well, here it's a little bit simpler. There's not so much to do. This will move across. Here we can factor out. So we get partial z, partial y, 1 plus, I'll rewrite it as x e to the xz is equal to minus x cosine xy plus 3y squared. And therefore, partial z partial y is minus x cosine xy plus 3y squared all over 1 plus xe to the xz. The fact that the denominators match up, that's actually not surprising. They should. They're both coming from the same part of the formula, that f sub z. All right. Well, once you get the hang of it, these aren't so bad. Well, now that we've done one problem, let's really go for it. So suppose you have the following. F of x, y, z equals 0. Find partial squared z, partial x, partial y, in terms of derivatives of f. Now, just as a reminder, we've actually done the first order derivatives. So remember, we said, hey, if I want to find just partial z, partial x, that's not so bad. I can find it in terms of the derivatives of f. Partial z, partial y, same deal. I can do it in terms of the derivatives of f. So why not second order derivatives? Well, the answer is of course we can. Of course we can. But let's just remember what's happening. So we have our diagram. So we're going to think of z as a function of x and y. So that's going to be important as we go through the whole process. So that we have that f depends on x, y, and z depends on x and y. So, where do we start? Well, we'll start the same the same way as we did before. So I'm going to take the derivative of both sides with, let's take it with respect to y. And so if we do, well, the derivative of 0 is going to be 0, so that's no big surprise. So take the derivative of the left-hand side with respect to y. Now when we come over to the diagram, what do we see? Well, we see y showing up in two places. So we're going to see that, okay, the derivative of the left-hand side with respect to y, that's f sub y, so there, plus f sub z, which is that part, times partial z partial y. So that's the derivative of the left-hand side with respect to y. And that's going to equal 0. Now we say, well, that's fantastic. We've gone partial z partial y. And if we've gone partial z partial y, we're kind of halfway there. Because the way you get to partial squared z partial x partial y is you start with partial z partial y, and you take the derivative with respect to x. So we say, aha, let's take the derivative with respect to x now. So in our first step, we took the derivative with respect to y. So now we're going to take the derivative with respect to x. So there comes a question here. F sub y, what does that depend on? Well, it turns out that f sub y has the same structure, because f depended on the three variables, x, y, and z. So again, f sub y still depends on those same three variables. And looking ahead, same thing with f sub z. So once you know what a function depends on, in other words, what variables it depends on, and you take a look at derivatives, you still know what variables it depends on. So f sub y, remember we're taking the derivative with respect to x. So we're going to take that derivative with respect to x, so I can think of this as f sub y, take that with respect to x, plus f sub y, take that derivative with respect to z, times partial z partial x. And this is the first term, plus, now we have f sub z. Well, it's the same process. So it's going to be, since we're doing it with respect to x, because x shows up in two places. In fact, it showed up in two places up here as well. We should have marked that. So what do we have? Well, it's f sub z with respect to x, this part, plus f sub z with respect to z times partial z partial x. And so that's the derivative of the first term times the second term, partial z partial y. Then of course we add to that the first term, f sub z, times the derivative of the second term. That's partial squared z partial x partial y. Ah, good. Well, actually, we're not done. That's the left-hand side equals the derivative of the right-hand side, 0. Now we're looking at this and we say, okay, what can we do? Well, there's a couple things we can do. We have a partial z partial y. How do we handle that? Well, the answer is we can use this formula. We can say that partial z partial y is equal to, if we come through here, that would be negative f sub y over f sub z. So that's going to be what this part becomes, negative f sub y over f sub z. What about the partial z partial x's? What do we do about those? And the answer is we say, okay, let's go back to our original formula and take the derivative of this with respect to x. And if we do, we're going to get f sub x plus f sub z times partial z partial x equals 0. So I'm taking the derivative now with respect to x, which tells us that partial z partial x is negative f sub x over f sub z. All right. Well, so that says this term, that's negative f sub x over f sub z. And that term, that's negative f sub x over f sub z. Well, what's the news? This is great news, because now everything is partial derivatives of f except one thing. And that's the one thing we will want. That's great. Good. Well, we still have to clean this up. Okay, so how do we clean this up? Well, let's start by saying there's going to be some fractions here. So we're going to multiply both sides, everything, by f sub z squared. That will get rid of the fractions that comes from there. Okay, so first step, let's multiply everything by f sub z squared. So we're going to times everything by f z squared. What do we get? Well, okay, let's work it through. So from the first term, well, we're going to get fyx plus fyz times minus fx fz times fz squared. Again, we'll clean this up in a second. Don't worry, we'll get there. Plus, second term, fzx plus fzz minus fx over fz. Then we have minus fy over fz. And then we're going to have an fz squared plus fz cubed times partial squared z, partial x, partial y, all equals 0. Okay, let's clean this up. Multiplying through, we're going to get fyx fz squared. And here, we're going to get minus fyz fx fz. Because you can see here that we're going to get one of the fz's cancel. Okay, so that's fine. Now how about here? Well, one of the fz's will cancel there right away. So we have an fy and an fz. And that's going to multiply through. So we're going to get a minus from here, fxz, sorry, fzx, then fy, fz. Then minus makes plus. There's another fz, that'll cancel with that fz. So we're going to get a plus fx, fy, fzz plus fz cubed times partial squared z, partial x, partial y equals 0. Now we're in the home stretch. We'll take all that, move it to the other side. So, rearrange. F z cubed, partial squared z, partial x, partial y is equal to, well, let's put the positive terms first. So we get the fx, fz, fyz plus fy, fz. And here, it doesn't matter which order I take it, so I'll do fxz. Okay, then minus, let's say this one, minus f, and I'll put xy. It looks nicer that way. Fz squared. Then here, minus fx, fy, fz, z. Now, one more step. We want to get rid of that fz cubed, and so we divide, and now we're ready to write down our final answer. So, we get partial squared z, partial x, partial y is equal to f sub x, f sub z, f yz plus f sub y, f sub z, f xz minus fxy, fz squared minus fx, fy, fzz all over fz cubed. And that's it. Wow. Okay, now, should you memorize this? Oh, no, absolutely not. Never. But you should know the process. And the process is just Be methodical. Work through it one layer at a time. On a side note, this was actually on an old exam. So I put this on a multivariable calculus final back when I was at UCLA. And I had two TAs, very smart. At least one of them is a professor now at a university someplace. And they both got this problem wrong. But some of the students got it right. And so, don't underestimate your ability. Sometimes you're even better than the TAs. Don't say I said that. All right. Well, good. Now that we've done the hard work, back to the easy stuff. And we'll do that next time.